Hello everyone. Here is the exercise class 5, which are about the Riemannian geometry and curvilinear coordinates. So before this exercise class, I expect that you to finish these two problems by your own, and then to watch this exercise class video then. So basically, we assumed you have finished your problem set 6 in order to deal with the curvilinear coordinate system to figure out how to calculate the crystal symbol and how to make use of the covariant derivatives. So let's start now. And our exercise class is going to make sure you understood each step of the answer. And then if you finish the two exercises, and you should watch it later to check out your answer. And it involves some physical concept that I want to introduce next, like the Riemannian tensor. So for the first question, we have to going to test you whether you are familiar with the covariant derivatives. So basically, we use the geometry of the surface of the sphere, where we have such a line element with the ds square, and a vector v with component v mu equal to 0 and 1. And then we have to calculate the covariant derivatives of the vector and also two different quantities. And then to discuss what is the why these two quantities are not commute to each other and the physical picture about the non-community. So, and then here is our first question answer. Make sure you have finished this question beforehand. And we adopt to the spherical coordinate and fixed R equals A. We have such a ds square line element. First of all, we have to write down the metric tensor in order to calculate the covariant derivatives. So basically, it's equal to, we only have the g of theta theta and g phi phi component. And then we have to go through the covariant derivatives with the vector, which just basically corresponds to the covariant derivative of the one-third tensor. If you're not familiar with the formula of a covariant derivative, you have to know it. You can find it in your lecture notes or your textbook. And in problem set 6, you have found out the spherical coordinate crystal symbol. So I don't calculate it again. I just show you the answer about the theta and phi coordinate of the crystal symbol. And then you have to calculate 4 different components of the covariant derivatives of the vector mu, because it has 4 different answers, because we have 2 different indexes in this covariant derivatives, and each of them has 2 choices of the coordinates. And then we, after we calculate these 2 and pop in this answer about the v phi equals 0 and v theta equals 0, v phi equals 1. And then we have to calculate the part B, calculate the double covariant derivatives of the vector theta component. First of all, we have to do the covariant derivatives with theta phi in the order, and then with opposite order 5 theta covariant derivatives of the theta component of vector. So here in the star expression, if you want to know it, you can derive it by yourself. And after the calculation and pop in different answer inside it, you can obtain the psi theta square, and this 5 theta 1 is equal to 0. Obviously, the part C is going to ask you whether it is commute to each other. It's obvious it's not commute to each other. So in this exercise class, I really want to tell you what is going on, why they are not commute, and which is just basically, intrinsically, the definition of the Riemannian tensor. So in the textbook is something, there is a equations about the commutator of the vector, and then the commutator like the theta phi with different opposite direction to the covariant derivatives, and then this commutator which exactly divided to be Riemannian tensor. And you just check out the Riemannian tensor for spherical coordinate 2D system. This guy is just basically equal to sine theta square, which exactly the answer with the equal to the commutator of these two covariant derivatives. So what is that mean exactly? So in the following, I have to go through some concept about how you define, how a old mathematician in the past define a Riemannian tensor. And here is a sphere and a fat paper. And if you originally define a vector, okay, I assume you have already learned what is parallel transport. If you want to transport through this direction and then this, okay, you can see the blue line here, the blue line with vector is vector, and then to become a different orientation as it transport. And then the blue would transport into this like termination point, right? Here is the termination point. And then the orientation of this basis vector would transform. And then if you try another path with the red line, the basis vector transform like here, you can follow this path and then transform to this termination point again. The orientation would be a difference again, because after you do a parallel transport under a curved linear coordinates, the basis vector would the orientation of the basis vector would transform as how you choose the roots. If the roots or the path are different as you choose, the orientation at the termination point would be different after you do parallel transport. Otherwise, here is a fat space-time, a fat paper. If you do the parallel transport in two different paths, like this path and this path, okay, you would be obtaining something like this. It would not change anything with two different paths, right? After you do 2 times parallel transport with 2 different routes. So, because these differences of the orientation are exactly due to the curvature itself. And then some mathematicians like Riemann has noticed this, and he wants to define a quantity which express what is the curvature, the amplitude of the curvature. So how, like, we introduce a just arbitrary curvature space-time. If the back line is the basis vector E beta, if we want to like at this point we have to allocate 2 different coordinate system, like the red line x mu and the blue line x mu along the surface. if you want to like do a parallel transport along these two directions would be transformed, and then will be something like this. Okay. Yeah, maybe I my drawing is very bad, so don't mind it. You know that if you imagine the back arrow would slide against the curved line, and then it would change the orientation of the arrow. So again, the red line, we try the red line to be another path to do the parallel transport, and the red line would be this, something like this. Okay, redraw it. Finally, would be something like this. Okay, and then you can see. Sorry about that. You can see there's two differences between these two vectors at the termination point. Okay, these differences, and then we might has defined a arrow to illustrate these differences between the two vectors after the two parallel transport with two different woods. And then here is the outcomes of the remaining tensor R. If under a flat surface you try these different two directions, okay, the arrow would be overlap to each other, and this is no differences for the for two arrows. So basically, it means the remaining tensor is equal to 0. So if you want to see how mathematically derive it, basically, like the R factor is just basically the like you have learned the coordinate transformation, right? If I want to transform from this point to this point, you have to multiply these two. First with is this point first, transform to here, and then this point. Okay, 1, 2, 3, and here is the is 1 and 2. Here is the I make some typo. Yep. If you want to transform to here, first step and the second step, you can see is the first step you do a coordinate transformation d with respect to mu in the second step. Okay, for this the same basis vector beta. And minus the, because we have to figure out the differences, right? What minus the differences to be mu and the nu. So along the mu, the first step and the second step. Okay. 1, 2, and here is 1, 2. Okay, two different paths to see two different paths with different coordinate transformation with different order. And then basically you have learned the coordinate transformation of the basis vector is just the Christoffel symbol times the basis vector. And after some step, actually you can do that by originally do with this formula. You can figure out the full expression of the Riemann tensor, is which exactly you have seen in the textbook. All right, now you figure out why the non-community of the two covariant derivatives because they are in different order. In different order is in the way is that they transform the basis vector in different roots, and then which means exactly means the covariant derivatives are with different order. Yeah, but sorry, in the opposite order. Like you calculate the theta phi first and or the phi theta in the part B. So here is our part B. It's just going to see what is the symmetry properties of the Riemann tensor and how to see the Bianchi identities. So for the second part, second question B, for the part A is just basically we have write down it. I just want to show you all the steps in times a metric tensor to make the superscript down become the subscript, and express the Riemannian tensor to be in terms of the metric tensor. All right, this finally would be equal to, and the metric tensor times inside the FE G mu nu, you can obtain something like this. If you calculate the minus sign of the alpha mu nu, and you can obtain the minus G alpha mu beta mu mu. And the things is just keep going by yourself. I hope you can do it. And later on, I can post the solution in the backboard. You can see by yourself. Here is just basically some mathematical trick. Yeah. Finally, you can see how it has the anti-symmetric property after you reverse these two indexes. So for the part B, C, D, I would post it into in backboard. You can just see by yourself. It's very trivial. This is the end of the exercise class 5. Thank you.